Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be starting a new unit, Unit 3. Specifically, we're going to be doing Unit 3, Lesson 1 on what's known as the triangle inequality. Now, Unit 3 is all going to be about learning how to explore physical space, strangely enough, through the use of triangles. Because triangles are really critical. And you might think, well, why triangles and not quadrilaterals or five-sided figures or things like that? Well, we're going to get into that a little bit today as we explore different configurations that 3 points in space can have and what that sort of tells us about space itself. So let's get right into it with the triangle inequality. Now, we start today with a very fundamental assumption about space. Let's talk about that. Fundamental assumption about distance. The shortest distance or shortest path between any 2 points in the plane is the length of the straight line segment containing the 2 points. Now, I really have to sort of like hammer this home, right? It's probably something that seems very obvious to you. But this idea, if I have 2 points in space, they could be in a plane or not, it doesn't really matter. If I have 2 points in space and I want to travel the shortest path from point A to point B, then that shortest path is going to be a straight line segment that connects the 2 points. That means if I do anything else, right, if I go in any other path, for instance, let's say I went in this path, right, then if I added up or if I unwound that piece of string, what I would find is that that's longer than line segment AB. In fact, to go a little bit further than that, if I even did something like this, if I took a third point out here and I got from A to B by, first going to that point up there and then going that way, well, then that would still have to be a longer path than just going from point A to point B. So this is an amazingly important assumption about physical space, all right? And we're going to be coming back to it quite a bit in this lesson. So let's take a look at exercise number 1. In the diagram below, points A, B, and C are collinear. Write an equation that relates the lengths of segment AB, segment BC, and segment AC. All right, we've already done this a little bit before. See if you can write down an equation that relates the lengths of AB, BC, and AC. Why don't you go ahead and do that? All right, let's go through it. Now, this is probably pretty obvious, right? Which is if we have 3 points that lie in a straight line, then the distance from point A, from the starting point, to point C, the ending point, is equal to the distance from point A to point B, which is just some point in between, plus the distance from point B to point C, right? So in other words, I can say, let me go back into my blue now, I can say that AC is equal to AB plus BC. All right, that is always true if the 3 points lie in a straight line segment. Now, again, make sure you really understand this. You can look at this AC as being the length of line segment AC. But more importantly, you should really look at AC as being the distance between point A and point C. And it's important to think of it that way because, again, if these weren't collinear, if we had, let's say, these 3 points looking like this, all right, then the distance from A to C wouldn't necessarily be the distance from A to B plus the distance from B to C, right? This would no longer hold if we had a situation like that. And we'll talk about this situation in just a moment, all right? But that is not what we're talking about here. All right, so let's now talk about the 2 configurations that 3 points in space can have. So 3 points in a plane can only lie in one of 2 distinct configurations. Either the 3 points are collinear, which is what we just saw, or they're not collinear, right? I mean, that's always kind of true. They're either blank or not blank, right? When the 3 points are not collinear, they can be connected with line segments to form a triangle. Obviously, if they are collinear, which was the situation back here with these 3, you can't form a triangle, right? That's what we would get. That's not a triangle. On the other hand, if the 3 points aren't collinear, they can be connected to form a triangle. All right, so let's take a look at exercise 2 right now and see what we're getting at here. In the diagram below, the 3 points shown are clearly not collinear. Using a straight edge, draw segment EF, segment EG, and segment GF. All right, why don't you go ahead and do this really quickly. Okay, simple enough, but I gotta do it too. So let me real quickly draw our 3 segments in, right? And all we're doing is connecting these segments with straight line paths. That's it. Granted, once we do that, what we end up having is this figure that we affectionately know as a triangle. All right, well, maybe we don't affectionately know it as a triangle, but I know it affectionately as a triangle. All right, great. So let's talk about letter B. The length of EF is the smallest distance between what 2 points? Now I know that this sounds silly, but seriously, right? It's the shortest distance between points E and F. All right, and again, I really need you to feel this in your bones, right? If I was going from E to F, the distance I would have to travel is the length of segment EF, if I was going the shortest distance. Now, if I wanted to go the longest distance, well, that would be an infinite distance. You know, I could like take off from E, go through the universe, and come on back to point F. Anyway, let's take a look at letter C. What does the inequality below mean graphically? EF is less than EG plus GF. Well, let's talk about this, right? I mean, EF is the length of side EF, EG is the length of side EG, and GF is the length of side GF. So what this inequality says is that the length of side EG is less than the sum of the lengths of the other 2 sides. The length of EF is shorter or is less than the sum of the lengths of the other 2 sides. Letter D. Why does the above inequality make sense in terms of our fundamental assumption about distance? All right, so let's kind of go back up here. Why does this inequality make complete and utter sense when we think about that fundamental assumption that we have about distance? Pause the video now and see if you can write something down. Well, you can almost talk about it as if looking at it kind of like in contradiction. What I mean by that is, let's say this wasn't true. Let's say that EF was not smaller than EG plus GF, right? Well, if EF wasn't smaller than these 2, let's say EF was larger than those 2, then you could actually get from point E to point F by going through point G instead, by going through a path that isn't the straight line path, right? All this thing is saying is, look, the shortest distance from E to F, right, is just going along the line segment E to F, and it must be shorter than first going through some point that doesn't lie on EF, right? So I'm going to phrase it like this. I'm going to say if EF wasn't less than EG plus GF, then there would be a shorter path going through G, right, to get from point E to point F. right? So if EF wasn't smaller than these two sums, well then we could take a shorter path, right, by simply going, I'll go to G first, then I'll go to F, right? If EG plus GF was smaller than EF as opposed to larger than it, which is what this says, then that would be the shortest path. Now I am kind of leaving the equals case out, right? What if EF is equal to EG plus GF? Well, if EF is equal to EG plus GF, well then that means that they're collinear, that G must lie somewhere on that segment in order for EG plus GF to be equal to EF. So not only does EF can't be like, not only does it have to be less than, it can't even be equal to those two sums. Let's go all the way down here. It says write down two additional inequalities that are similar to the one shown in C. Well, let me write down the one shown in C really quick. The one shown in C is EF must be less than EG plus GF, right? And that's, again, basically it's just saying, right, the shortest path from E to F, right, is line segment EF. In other words, right, EF has to be smaller, that path has to be smaller than this path. Well, I can do that between any 2 points on this triangle. Let's do it for EG, right? So EG, to go from E to G, must be smaller than to go from E to F plus F to G, right? So to go from E to G, EG, that must be less than going from E to F and then from going F to G, right? And again, if it wasn't, well then this would be the quickest path to get from E to G rather than just going through there. Now the final one that we haven't done, let's say, is going from G to F, right? To go from G to F must be shorter than going G to E and then going from E to F. Okay? And all of this gets into one of the most famous theorems in all of geometry. I'm not even sure if it should be considered a theorem. It's called the triangle inequality. Let's take a look at the triangle inequality. The length of any given side of a triangle will always be less than the sum of the lengths of the other two sides. This is simply a restatement of the shortest distance between 2 points assumption. All right? So again, right, a lot of people treat the triangle inequality as some kind of crazy theorem. Oh, well, you know, any given side of a triangle must be shorter than the sum of the other two sides. But all that's saying is that, look, you know, if I take side AC, right, and I look at the distance from point A to point C, that has to be smaller than going from A to B and then from going from B to C and adding those together. That's all it is. So let's take a look at exercise number 3, where we think about the possible lengths of side AC. Exercise number 3. The triangle below is not drawn to scale. That's really key. Not drawn to scale means that you can't really base how big length AC is based on other stuff that you see in the picture. Okay, but the triangle inequality is still going to hold. Two side lengths are already given. Letter A. Could AC be equal to 40? Why or why not? All right, so again, you know, I can erase, hopefully you can too if you're working with pencil, right? If I put a 40 there, could that be the case? Could AC be equal to 40? Think about this for a moment, either from the perspective of the triangle inequality or from the perspective of you know, the shortest distance between 2 points being the straight line segment, et cetera, and think about whether that could be the length of AC. And the answer is no, right? And the answer is no because, right, 14 plus 25 is 39 and 40 is greater than 39. And again, like, don't worry about the triangle inequality. Just remember that whole shortest distance between 2 points thing. You could never have this situation because if you did, then to go from A to C, let's say these were all in inches, right? To go from A to C would only be 40 inches if you went along a straight line path. But if you put some random point out here, you could get from A to C quicker by going 14 inches this way, 25 inches that way, and that would only be 39 inches. So somehow we could get from A to C and a shorter path than that direct line path. So absolutely not. Let's take a look at B. Could AC be equal to 8? Why or why not? All right, so let me get rid of this and let me put an 8 in there. Well, could that be the case? Well, now, certainly, right, AC is shorter than the sum of these two sides, so that seems to be okay. But there's a reason why AC couldn't be 8 as well. Pause the video now and see if you can figure out why the answer to this will also be no. Well, this time it doesn't have anything to do with the shortest distance between A and C. This time it has to do with the shortest distance between B and C, right? So this time the answer is no, because 8 plus 14 is 22, and 22 is less than 25. So again, AC can't particularly be equal to 8, because if AC was equal to 8, then the shortest distance between point B and C wouldn't be the line segment BC, but it would actually be going up to point A first, then coming down to C and only having a distance of 22. So it also can't be equal to 8. So what values could it be equal to? Let's take a look at that in letter C and letter D. Use the fact that the shortest distance between B and C is equal to 25 to write and solve an inequality for AC. All right, so in other words, like given the scenario we have right here, let's just hone in on the largest number that's given. Right now, we know that the shortest distance between B and C is 25. And whatever AC is, when we add AC and 14, that sum has to be larger than 25. It has to be, right? But now this is about the simplest inequality you can possibly solve. I'm going to subtract 14 from both sides, and I'll get AC must be greater than 25 minus 14, so AC must be greater than 11. It can't even be equal to 11, right? Because if it was equal to 11, then of course those two sides would add together to be 25. All right, so whatever AC is, it's got to be greater than 11. Now let's take a look at letter D. Use the fact that the shortest distance between A and C is equal to AC to write and solve another inequality involving AC. So in this case, let's just hone in on AC itself, right? And one thing that we know is that whatever the length of AC is, it's got to be less than 14 plus 25, right? It has to be, right? Because again, it's the shortest distance between points A and C, so it's got to be less than summing those two distances, which means AC must be less than 39. All right? Now, notice that on the lower end, AC must be greater than the difference between the two side lengths we know. It's got to be greater than 25 minus 14. It's got to be greater than 11. And AC must be less than, on the upper side, the sum of those two sides. All right, based on C and D, write an interval of all possible values. Well, we can now write it like this. AC must be greater than 11 and less than 39. Any value in there, pick any number that's larger than 11, boom, but less than 39, boom, and all conditions would be met. You know, for instance, like 20. That's a nice number that's in between 11 and 39, right? And if we had 20, we'd be fine, because if I add 20 and 14, that's 34, that's bigger than 25. If I had 14 and 25, that's 39, that's bigger than 20. If I add 25 and 20, that's 45, that's bigger than 14. So, you know, the sum of any two sides always ends up being larger than the third side. All right? And that's a great way that will always work to find the possible values of a missing side of a triangle if I have the other two sides. I simply subtract them to find the lower end, and I add them to find the upper end. So let's see how that plays out. Exercise number 4. In triangle EFG, EF is equal to 18, FG is equal to 7. Which of the following values could be the length of GE? Well, like what we saw before, right? You know, we've got some random triangle, EFG, all right? We know that EF is 18. We know that FG is equal to 7. We want to know a possible value for that. Now, one thing that you could do is you could take each one of these in turn and just see if it matches the triangle inequality. Like, let's say I started with the smallest one, right? 4, okay? Well, that would be a problem because when I add 4 and 7, I get 11, and that's smaller than the 18, which again is a problem because that would mean I could go from E to F in a quicker way by going like this than by just simply going like that, right? So it can't be 4. All right. Now we could go through each one of these in turn and do that. But the cool thing is that we can say that EG must be greater than 18 minus 7. It's got to be, EG has got to be greater than 11. Okay. So anything below 11, it can't even be equal to 11. All right. Anything below 11 wouldn't work. All right. And likewise, EG must be less than 18 plus 7. So EG must be less than 25. So we're looking for a number that is greater than 11 and less than 25, and that's 20. All right, and again, you know, let's take a look at the upper end, right, the 28. You know, again, why couldn't it be equal to 28? Well, if I added the 7 and the 18 together, I would get 25. 25, right, is larger than 28, which means, again, if I was going from point E to point G, I could go a shorter path by doing that than just by doing that. And that violates that fundamental assumption about distance. But this is a real handy trick when working with the triangle inequality. If you've got two sides, right, and you want to know all the possibilities for the third side, subtract them, that's going to be your lower limit. Add them, that's going to be your upper limit. And then the actual value has to be somewhere in between. It can't even be those two. Those two are the ones that would force the 3 points to be collinear. Collinear. All right, let's look at one last problem. Exercise number 5. In triangle PQR, PQ is equal to 3 centimeters. QR is equal to 17 centimeters. The length of PR is an integer. Determine all possible values for PR. All right, great. Why don't you play around with this a little bit? All right, well, keep in mind, right, that we can kind of PQR, visualize this a bit. PQ is equal to 3, QR is equal to 17. We don't know what PR is doing. So we know that PR has got to be greater than 17 minus 3. So PR will have to be greater than 14. On the other hand, PR is going to be less than 17 plus 3, so PR must be less than 20. Now, there are an infinite number of values between 14 and 20, an infinite number of values, okay? We would never be able to list them all. But here it says that the length of PR is an integer, right? Meaning that it's a whole number. Here's where you need to know what the word integer means, right? Now, what is the first integer larger than 14? Well, 15, then 16, then 17, and I want to keep listing these until I get to the last integer that is less than 20, right? So the possible lengths of PR are 15, 16, 17, 18, and 19, and these are all centimeters. All right, so let's do some summary, right? Today we really looked at an important property in space, right? Which was that the shortest distance between any 2 points is equal to the path of the straight line segment that connects the two. All right, using that fundamental assumption then, we can come up with a really cool fact about triangles, which is that if you look at the length of any side of any triangle, that length must be smaller, shorter, less, however you want to put it, than the sum of the other two side lengths. It must be, right? Because if it's not, then the shortest distance between the 2 points that make up that line segment, or that are the endpoints of that line segment, the shortest distance between those isn't the line segment that connects the two, right? Now, one of the things that leads to is if we have a triangle where two sides are known and we want to think about what the third side could be, we simply subtract the two sides that we know, and that will give us sort of the lower bound of what that third side could be, and we add the two sides that we know, and that will give us the upper bound. All right. All of this falls into what we call the triangle inequality. All right. And it's an inequality because it's always, the length of any side is always less than the length of the other two sides summed together. All right, well, the triangle inequality, we won't see a ton in this class, but we'll see it kind of rise up here and there. But we're going to be working with a lot more triangles as we move on in Unit 3. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.